All right, so good morning, everybody. So today what we want to do is we want to learn, continue what you were learning in week 2 about correlation and expand on it with the topic with regression. How many people have their graphing calculator with them today? All right, well, I hope you guys do. We're going to use your graphing calculator a ton today. Now, I'm going to primarily load up the TI-84 emulator here today. If you have a TI-83, it's basically the same options. Okay, there's just like a subtle difference, and I'll explain that subtle difference as we go. I just like the TI-84 emulator here. So we'll actually start class with a bit of a review of what you learned in the online lectures last week. And then this week on your own in the week 3 folder, your post-class requirements. I have a review lecture here on regression, just kind of some more examples of what I talk about in class today. Just, if you want a different lecture that's, additional examples, it's there. And then you're actually going to learn on your own the basics of probability this week. Just like the real simple probability questions, like, what's probability of flipping heads on a coin? What are probability from a table of data? It's real simple stuff. And then your online quiz this week, as always, you have 2 attempts. Ignore this part. There's a little bit of a typo here. There's only 1 assignment. Sorry about that. It's 12 questions and it's half probability, half regression. Okay, so I promise you by the end of today's lecture, you'll be able to do the regression stuff no problem. And the probability stuff is really easy, to learn on your own, to be able to handle the quiz this week. Before I get started in the main lecture, does anybody have any questions about any of that? All right, everybody having a good day so far?
Yeah, pretty good, just tired.
Oh my gosh, I'm so tired. It's definitely a full pot of coffee day for me. Okay. So going into the classroom under week 3, under the course meeting materials, I posted this lecture file. I made one little change to it prior to class. When we get to that point, for anybody who downloaded it prior to class, I'll tell you where that change is. It's at the very end of the lecture. But I'm going to use this file right here. Okie dokie. Okay, so this week we're continuing and talking about this concept of correlation and regression. So first off, correlation from your online lecture. Correlation measures the strength of what? Does anybody remember what it measures? Of a what type of relationship?
Linear?
Yes, thank you. Okay, in this correlation, you saw on your own how to calculate this linear correlation coefficient R. And it's an incredibly complicated formula, so we're always going to use our calculator here. But the value of R is always bounded between what 2 numbers when you calculate it?
0 and 1.
Not close, not 0 and 1, but
-1 and 1.
Yeah, thank you, Heather. You got it there in the chat. Yep, it's always bounded between -1 and 1. Okay, so the value of -1 means, hey, I think there's a negative linear relationship between the variables. A value of 1 means, hey, I think there's a positive linear relationship between the variables. The important thing here is if you have a value of R close to 0, okay, it doesn't mean there's no relationship. Okay, it just means there's no linear relationship. Okay, we use this, as I said, to measure a relationship for a linear relationship between 2 variables. Okay, we call these two variables, we have our explanatory variable and we have a response variable. Okay, these are the two variables we're going to have. We're generally going to denote our explanatory variable with the variable x and our response variable with the value y. Okay, so we're just going to do a lot of x and y stuff today. All right. Now, I encourage you all as you're watching this lecture, I'm going to do this review example, and we're actually going to use this review example for the later stuff in class. So it's worth just following along and inputting the data into your calculator. Okay, so here's the example, and it's a lot like the data from the online lecture. I just changed it a little bit. All right, so your instructor and me is interested in seeing if the amount of time students spend studying influence their grade. Okay, so and let's just pretend that for last semester, for my statistics course, I sampled 8 students and I asked them how many hours of study they had, and then I looked at their corresponding exam scores. Okay, so how many hours they put into studying for the midterm exam. All right, so I have hours of study and exam score here. First thing here, I want to have 2 variables. I want to define what's going to be the explanatory variable, and which will be the response variable. So which is going to be my explanatory variable here?
The hours of study.
I agree. Thank you. Yeah, I think the hours of study explain the exam scores that people get. All right, so here's what I want to do. I want to create the scatter plot. Okay, of the data. So to do this, what I'm going to do is I'm going to load up my graphing calculator here. Okay, and if you've reset your calculator, or if you've changed the settings with the calculator with the online lecture, you don't have to change these. But I'm going to reset my calculator, and I'm just going to go back and I'm going to put on the settings that we need for this class. Okay, so if you don't have these settings in your calculator, you're going to want to follow along because we're going to use these settings a bunch. So if you remember from the online lecture, I said you had to turn this thing called diagnostic on. Does that ring a bell to people in the lecture that you watched on your own? Diagnostic on? Yeah, all right, thank you. So to do that, you're going to go to the catalog button. And you see all these crazy options. So you can either scroll down till you find D, or you can hit this button right here, the X inverse button. You see how it says D right there? I'm going to scroll down. I want my diagnostics on. Okay. All right. Now, as long as your diagnostics are on, do not ever turn them off. There's no reason to ever turn them off. So what I'm going to do is I'm going to take this data and I'm going to input it in my calculator. So next I'm going to hit the stat button. And under number 1, I'm going to edit the list. And in L1, always get your explanatory variable. So it's hours of study. So it's 1, 2, 3, 4. Oh, I'm missing a value of 5. Okay. 6, 7, 8, 9. And then in L2 gets the corresponding exam scores, and they have to go be grouped. They have to be right next to each other. So 50, 54, 60, 65, 78, 82, then 85, then 88. Okay. Now, because I reset my calculator, I just want to turn my stat plot on. So I'm going to go second function, stat plot here. And mine says plot 1 ... off. I'm going to hit enter and I'm going to turn it on. And this is the scatter plot right here. So the first option there is the scatter plot for your data. So whenever you input new data and want to see the graph of it, you just hit the zoom button. So zoom, and you want number 9 for zoom stat. Okay, so how many people were able to follow along with me here and see what I have?
I am.
Okay, good. Awesome. All right, so just looking at this relationship here, okay? I have this scatter plot in my graphing calculator. I would describe this as a positive linear relationship, okay? So we are seeing a positive linear relationship here. Okay, good. Now let's measure the strength of that. Okay, so now let's calculate R. Okay, so let's find the value of the linear correlation coefficient for this. Okay, so I forgot how to do this. Can anybody remind me how to calculate R in your graphing calculator from the online lectures? Does anyone remember?
Yes, you put in all your data. Oh, sorry.
Yeah, you can go.
I'll let the first person go. Go on ahead. You're right. I put the data in.
Oh, am I the first person? Okay, you put in all your data.
Uh-huh.
And so that's stat.
Stat.
And then you go to move it over to calc.
Perfect.
And then you go down to 4, I think it is.
Yep, you got it. Okay. Thank you. So you're exactly right, and I appreciate the help. You did a good job reminding me. Now I remember, I didn't forget. So for this week in your graphing calculator, the option we're going to use is linreg, and then you see this ax plus b. Always, 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 always. Okay, it's option number 4. I'm going to go to number 4. I'm going to hit enter. Now, if you have a TI-83 calculator, all it says on the screen now is linreg ax plus b. Just hit enter again. Okay, just hit enter. If you have a TI-84, you just scroll down to calculate, and you should see something like this. Okay. How many people have this on their graphing calculator? Okay. So we're going to talk about, there's 4 values there, A, B, R squared, and R. R squared, we're not going to really talk too much about in this class, but if you go further in your studies, you'll learn a lot about R squared. R squared is called the coefficient of determination. And what it means is, it tells you the percent variation in the response variable that can be explained by the percent change or variation in the explanatory variable. What the heck does that mean? Let me go back. Jessica, you go stat, you go to calc, and it's option number 4. Oh, you have AB. You forgot to turn your diagnostics on, Jessica. So go to second function, catalog, press the X inverse button, and you're going to scroll down till you find diagnostics on. Then you should be able to see this. Okay. All right. So R squared real quickly is called the coefficient of determination. And what it says is, it tells you the percent of variation in the response variable that can be explained by the variation in the explanatory variable. What I mean by that, do you notice how somebody who studied for 1 hour got a 50 and somebody who studied for 2 hours got a 54? Well, their grade difference was 4 points, okay? What that means is 98, almost 99% of that difference, that change of 4 can be explained by the 1 change in hour. Okay, that means there's like another 1% that can't be explained. Something else is causing that change, but it's really high. Okay. All right. So for us, what we're interested in is this value R. It's 0.9943. Okay, and this is really close to 1. So just by looking at that, since it's really close to 1, it means, yeah, for sure, we have this strong evidence of a linear relationship here. So here was the scatter plot. But at the end of your lecture, I showed you, or I talked about this thing called the correlation coefficient critical values, okay? Like, for example, this R value here is really close to 1. So it's very obvious that there's a strong relationship. But what if it was like 0.65 or 0.7? You know, like, is that enough evidence to say that there's a linear relationship between the values? So you use this thing called the critical values for the correlation coefficient here. So this table is in your slides from last week, but it's also here. All you do is you go to N. This is your sample size. All right, this problem had 8 students in it. This is the cutoff value. This critical value, think of it as a cutoff value. Kind of like the outlier cutoff value. As long as your value of R is greater than this number here, all right, you can say, yes, there's a linear relationship here, okay? All right. So since our value of R is greater than that 0.707, there's definitely a linear relationship between the variables. All right, so that was a quick review, but does this kind of ring a bell from the lecture last week on your own? Okay. All right, many of you watched the lecture last night, so it should still, you know, be in your mind. Okay, all right, let's do some new stuff. So keep this data plugged into your calculator. Don't change anything yet, all right? We're gonna use it in a bunch in class today. All right, so what's next? All right, so since we know there's a linear relationship between the variables, what we wanna do is we wanna describe or model the relationship with the mathematical equation, okay? So what type of mathematical equation are we going to use here? So we're going to use a linear equation or the equation of a line. All right, so this right here is what we're going to do is we want to fit this data here. You can see here this line. We want to fit the data with equation of a line. So we maybe remember from algebra class, this is our equation of a line. Y is equal to mx plus b. Okay, remember x here, that's our explanatory variable. For our problem here, what was our explanatory variable? We had hours of study, or was it exam score?
Hours of study.
Okay. We know Y is our response variable. Exam scores, excuse me. So then, does anybody remember what M stands for in the equation of a line?
Slope.
Yep, thank you. It's the slope. All right, the slope is also synonymous with a rate of change. And then what is the B?
The y-intercept.
Thank you. Okay, so the y-intercept. So what we want to do now is we want to find the line that fits the data, okay? Why might we want to do this? Okay, why might we want to find this equation, this y is equal to mx plus b for this line right here? So what we use it for, this regression line, is we use it to estimate for unknown values. Okay, for example, if you look at the chart here, okay, is there any value of 5 here? You know, no. Okay, so what we want to use this equation for is if if you're like the night before, okay, I'm going to study for 5 hours. What grade can I expect to get? Okay, it's going to be somewhere between a 65 and 78, obviously, but like what exactly? Or if you notice there's no 10 here, okay, what grade would you expect if you study for 10 hours? Okay, that's the whole point of regression. Okay, so we use regression, or excuse me, I'll use regression here incorrectly right now. We use the linear model to estimate or predict, that's another word I'll use a lot today, or predict for unknown values. Okay, that's the whole point of this linear model that we're going to put to the data. Okay, so we want to find this nice equation of the line. Okay. Okay, so to do this, what we're actually looking for is what's called the best fit line. Okay. So if you wanted to put this data, a line that best fits this data, okay? If you just look even in the first quadrant of the Cartesian plane, there's an infinite number of lines you could choose, okay? Like you could pick that line. Does this line fit the data well? Do you guys think?
No.
No, it's terrible, right? Does that one fit the data well?
No.
No, nope. How about that one?
Nope.
No.
No. Okay, so this one, nope. So this one seems to fit the data well, okay? So the question now becomes, there's an infinite number of lines, okay, that I could pick. Okay, how do I find the line that is the best line, the line that literally best fits the data? And it turns out of all the infinite lines you could pick, there is literally only one line that is the best fit line, okay? Okay, so we can use this best fit line or least squares regression line. So you'll hear me say this synonymously with each other, best fit line or least squares regression line, okay? So this concept of LSR, least squares regression, is how we find the best fit line. Okay, so what the heck is this least squares regression, okay? So least squares regression, all right, is the line that minimizes the sum of the squared errors. Okay, so we have this concept now of errors or residuals. If you're going to take away one thing about what the heck is a least squares regression line, okay, this is all you really have to remember, okay? It minimizes the errors, okay? All right, I'm going to explain to you what the errors are in a second, okay? So the line minimizes the sum of the squared vertical distance between the observed values of y and what we call those predicted by the line, which is given by this notation here. Y with a little hat on top of it, okay? We literally call this y hat, okay? And what this is going to be is this is going to be y predicted, or sometimes you'll hear me call it y estimated. Okay, I'll use those interchangeably, okay? So what I mean by that, this y hat, okay? This line right here, this red line, best fit line, we denote as y hat is equal to mx plus b. Now look at the line. Did the line touch every data point? Like exactly, did it touch every data point?
No.
No, it doesn't, right? Like, look right here. Okay. This is an X value of 1, 2, 3, 4, 5. This is an X value of 6 right here. And the data point, if you look back on the table, let me go back just real quick. Someone who studied for 6 hours, the actual value they got was a 78. But this line is the line that models the relationship or predicts the values. Okay, do you notice that for somebody who studies for 6 hours, the model is saying they're going to get this amount on the exam? Right here. Do you see how it's a little bit lower than the actual value? Does that make sense to everybody?
Yeah.
So if you notice, did the line get it right? Like, did the line actually predict what somebody who studied for 6 hours would have gotten? Like, no, it didn't. Okay, so what's going on here is the equation made an error, okay? And so all this does, and let me show you another visual representation of these errors, okay? Kind of zoomed in on it here. Here was the actual value that the student got, okay? I think I said it was a 78. The line is below it, okay? So let's just say, I don't know if this is what the line actually says, but let's just say the model says the student should have got a 66, okay? That difference, this error, which is the difference between the real value and the predicted value, is 2. So the model was off by 2 points, okay? Do you notice, like looking at it here, there'll be an error 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 here, here, and there'll be an error here. Like each one of these will make an error. So this is all the best fit line is. It takes all the errors that you could make, because some are going to be positive and some are going to be negative. It squares them and sums it up. And this is the line that just minimizes the errors, okay? All right, it just minimizes the errors. It just makes the sum as small as it can be, all right? Because like, for example, if you had picked this line as your best fit line, the errors would be so much larger, right? So when you squared these and summed them up, you would get such a bigger sum than this. All right, so this regression line, this least squares regression line just minimizes the errors, okay? So does that kind of make sense?
Yes.
Well, thank you for the one yes. I appreciate it. Everyone else is zoning me out and getting coffee. Okay. I hope it makes sense. It's just a line that minimizes the errors, Okay.
It makes sense. I'm just paranoid that I'm going to unmute myself accidentally. So I hide my mute button.
You're okay. You're okay. Look, you know what? To put everybody at ease, all right? You guys see my video here, okay? This is what newborn life looks like, okay? So you shouldn't be embarrassed at all, okay? This is messed up, haven't shaved, tired. So don't ever feel embarrassed, all right? I hope everybody got a laugh out of this. No laugh, okay. No pity LOL.
I laughed.
Thank you. Okay. Look, you can have a little glimpse into my life. You're looking back at my screen. Here's Yoda. Yeah, there's an X-Wing. This boat here, is that the one you're referencing? Some boat right there? My wife, when we first started dating, said she would get me a boat for my birthday. Okay. So this was the boat she got me. Okay. I thought she was going to get me a real boat, but she got me this little plastic guy. Okay. All right. You guys are like, just get on with the lecture. I just thought I'd, liven it up and make you laugh a little today. Okay. Here's just another visual of this. This is just a different example, just so you can still see this idea of a residual or an error. Here's another line, okay, and these are actual data points here. If this is the real data value, okay, right here, and this is the predicted value on the line, okay, that we call y hat, okay? If you just take the real value and this model says, you know, the real value is 5.2 and the model says you should have got 4.75, this difference is the error. That's all it is. All right. So there's three ways we can do this, all right, to find this equation of the regression line. Okay, so the equation of the regression line is y hat is equal to mx plus b, okay? There's three ways we can do this. We're gonna show you, first I'm gonna show you how to do it by hand, okay? Then I'm gonna show you how to use your calculator. I just like doing it by hand once just so you can see exactly how this is calculated. But then going forward, we're always going to use our calculator. And then you can use Microsoft Excel to do this. There's an online video in the classroom for this. Okay, so if you're interested in seeing how to use Excel for this, you can do that on your own, okay? But we'll focus mostly on the calculator here. All right, so this is the equation here, all right? So this is the equation for how you find the least squares regression line by hand, okay? All right, so the equation is this: y hat is equal to, when we do it from the online textbook, this is the formula, okay? B1, this is the slope. So they just call it B1 instead of M, okay, but it doesn't matter. Times X, okay, your explanatory variable, plus B0 is the intercept. Okay. So when you do this by hand, the first thing you're always going to find is you're going to find the slope first, always. Okay, so B1, the formula for this is R. Okay, does anybody remember what R is? Did we calculate it already? I think it was, yeah. Thank you, Heather. It was the correlation coefficient. Okay, all right. So R is the linear correlation coefficient. So we already have that, okay? You're gonna take R and you're gonna multiply it by S sub Y divided by S sub X. All right, does anybody remember, maybe from the online lectures, what S stood for in statistics? S.
Sample set?
Sample, not set, sample.
Standard deviation.
Yes, standard.
Size.
Yep, you got it. Sample standard deviation. So S sub Y, S sub X is the sample standard deviation. Okay. When you see the subscripted Y, that means it's the standard deviation for the Y value. When you see it for the X, that means it's the standard deviation for the X values. All right, so it's R times the standard deviation of your Y values divided by your standard deviation of your X values. Ugh, okay. Next, after you that, then you find the intercept. Okay, and it's Y bar minus, that's why you needed to find the slope first, because the slope is in the formula for the intercept, okay? Y bar minus the slope times X bar. Does anybody remember what X bar stood for in statistics? Sample.
Sample mean.
Yep, that's it. Thank you. So X bar means the sample mean for the X variables. What do you think Y bar means then? Well, whenever the bar above the variable means the mean of the X variables, Y bar just means the mean of the Y variables. Okay. So I also have this here. Okay, so x bar is the sample mean and s sub x is the sample mean of the explanatory variable x. Y bar is the sample mean and S sub y is the sample standard deviation of the response variable y. Okay, so that's it. So to do this formula, okay, all right, this y bar is equal to b1 times x plus b0. You need 5 things. You need to find r, the linear correlation coefficient. You need to find x bar. You need to find S sub x, you need to find y bar, and you need to find S sub y. The good news is we'll use our calculator to do these, okay? All right, so let's go back to our example from the previous slide here, okay? All right, so what I want us to do here, let me just see where we're on the slides, okay. First thing I want us to do is find the equation of the least squares regression line, okay? And that least squares regression line is y hat is equal to b1 times x plus b0. All right, we've already said that the hours of study is our explanatory variable. And the grade is our response variable, or the y. Okay, so to do this, we're gonna need to find r. Can anybody look back in the notes and tell me what r was? We'll go to 4 decimal places here. I think it was, yep, 9943, thank you. So next, what we just need is we need these 5 values, okay? Grab your trusty calculator right here. You have the data plugged into your calculator, all right? So everybody hit the stat button on their calculator now. And I want my calculator to do all this crazy calculations for us, all right? So I'm gonna go over to calc. And this example has 2 variables, okay? It has an x variable and it has a y variable. So I don't want 1 dash var stats. I want 2 dash var stats, okay? So I'm gonna go scroll down to the number 2 here. I'm gonna hit enter. Now, if you have a TI-83, it just says 2 dash var stats here, just hit enter again. I'm gonna go down to calculate here. I'm gonna hit enter again. And you should see something like this, okay? How many people see this on their calculator? All right, great, awesome. And look at this, X bar. What's the average amount of time that people spent studying?
5.
Yeah, do you see S sub X right there? The standard deviation for X was 2.9277. I'm gonna scroll down. I see Y bar. Wow, this is awesome. Y bar is 70.25. And the standard deviation for the Y variables was 14.8204 when I rounded to four variables, okay? So I'm gonna go write this stuff down for us over here. X bar from our calculator was 5. The standard deviation was 2.9277. The average exam score was 70.25. And the standard deviation for exam scores was 14.8204. Okay, so to do this by hand, all right, I have to find B1 first. I have to find the slope. So that was just R times S sub Y, over S sub X. Sometimes, S sub Y over S sub X. So all you have to do is just plug this in. Okay, this is just a plug and chug. It's 0.9943 times 14.8204 divided by 2.9277. I'm going to quickly do this in my head. Can somebody with a calculator verify? It should be, carry the 1, 5.0333. Did I do that right? Wow. You guys believe I did that in my head?
Crazy.
All right. Okay, it's a bad joke. I have the answers written down right here. Okay. Just trying to save us some time. So that's the slope, okay? So my slope I know is 5.0333 times x, okay? Plus, now I got to find the intercept, b sub 0, okay? That's y bar minus the slope times x bar. That's why you found the slope first. So that's 70.25 minus 5.0333 times x bar, which is 5, which will get you 45.0835. Okay. So actually not too bad doing it by hand, right? So just so we're clear here, okay, this y hat, okay, this is my estimated or predicted exam score, is going to be equal to 5.0333 times x, which is the hours of study, plus this 45.0835. Okay. Let's verify now real quick that the line actually fits this data well. Okay. So everybody grab their trusty calculator again. So what I want to do just to see how well this line fits the data, I want to plug the line actually into my graphing calculator. So everybody hit the y equals button on their calculator. All right, this is how you're going to put the equation of a line in. Notice how it says y1 is equal to. Now what we're going to do is we're going to input this equation in right here. We're going to put the slope, 5.0333. Now to put the x variable in, all right, on your graphing calculator, do you see this button right here? Okay, where my mouse is? It says x, comma, t, comma, theta, comma, n, right here. All right, press this button, and you'll notice it puts the variable in there for you. Plus 45.0835. And I'm just going to hit enter. And now I'm just going to press the graph button on my calculator. And how many people see this on their calculator right here? If you were following along. All right, awesome. Wow, look at that. Does this line fit the data really well? What do you guys think? Yeah.
It does.
Yeah. So guess what? We just found the best fit line by hand. Okay, so it turns out there's legit no other line that best fits the data than the one we just found. Okay, so we found the equation of the line that like perfectly models it. Okay.
I have a question. Mine doesn't look like that.
What do you mean? Look like blue?
No, it just like looks like it goes straight up. Like it doesn't look like that line.
Could you say it a little bit louder? Why does it look like it goes straight up?
It looks like it goes straight up. Like it doesn't look like the line I'm seeing on yours.
So did you press Y? Oh, I know what you did. Under Y equals, do you not have this X right here?
No, I do.
So you have 5.0333 times X. You press this button.
Yeah.
And then you have plus 45.0835.
Yep.
And when you press graph, is it a vertical line or a horizontal line?
It's a vertical.
It's a vertical line. And when you have this Y equals, you see Y1 here?
Yeah.
I'm not sure. Maybe after class, when we end class, we'll reset your calculator together and we'll do all this, okay?
Okay, thank you.
Yeah, no problem. And just remind me at the end of class, okay?
Okay.
All right. So for now, all right, it looks like it fits the data well. So now let's answer some questions, okay? All right, so going back, now let's plot the line on our calculator. Does the line fit the data well? Just to go back and answer this, yes. Fits the data very well. All right, I'm just gonna put in parentheses, good job, Matt. Okay, give myself some accolades there. Okay. So the next sentence says, use your least squares regression line to estimate an exam score for someone who studies for 5 hours. Okay, so this was our equation. Y is equal to 5.0333 times X plus 45.0835. All right, can anybody tell me how we might use this line, this equation here, to estimate someone who says, hey, I'm only going to study for those 5 hours?
Yeah, you just plug in 5 to the X.
Yeah. So remember, X is the hours of study. So all you're going to do is plug that into the equation. Okay, so I get Y hat is equal to 5.0333 times 5 plus 45.0835. Just in this example, it ended up working out where this is Y bar, but that's not how it'll always work out, just so we're clear. And so we see that, hey, if you're only going to study 5 hours for the exam, I predict or estimate that you're going to get a 70.25. Okay. Not too bad. Now let's predict the exam score for somebody who studies for 10 hours. Okay. How are we going to do there?
Same thing.
Yeah, same thing, except here we're just going to plug in X is equal to 10 into our equation. All right, so Y hat is equal to 5.0333 times 10 plus 45.0835. This person here is going to do very well. They're going to get a 95 when you plug this in your calculator, 0.4165, I believe. Okay. All right, so for these two questions here, pretty straightforward how to do this. What do you guys think? Thank you, Heather. Okay, got some yeses. All right, so now this is a weird question. Find the residual, okay, when X is equal to 4, okay? What was another word I called residual in this lecture? Thank you, Heather, yep. All right. What was the equation for this? I think it was, if you look back in your notes, it was the actual Y observed value minus what we call the Y predicted or Y estimated. Okay, so the error, I'm just going to call E, is the actual Y value minus the Y predicted. Well, Y predicted we denoted as Y hat. All right, so look back at the table here. Okay, I'm going to go back for a second here. Okay, when somebody studies for 4 hours, what did they actually get on the exam?
65.
Okay, so that's our Y actual value, okay? Where are we? Right here. How do I find Y predicted? How do I figure out what the model says I should get for when X is equal to 4?
how far it is from the line.
Okay, yep. But so I have to find the equation, I have to find the value of the line when x is equal to 4. How will I do that?
You can plug it into the LSR.
That's right. Yeah. So let's see. So the actual observed value the person got was a 65. Okay, let's find out what the line says, the model says the person should have got. So y hat is equal to the slope times the number of hours they're going to study. Well, they're going to study for 4. Just like this. All right. If you plug this in your calculator, you'll end up getting 65.2167. Which means the model made a little bit of an error. It was off by, it overestimated what the student would get by 0.2167. And that's it. What do you think? We're going to get to do this more. Okay, so don't stress. But right now, does it look kind of reasonable?
Yeah.
Okay, I got 1 yes. I got 2 yeses. All right. So the next thing I want to talk about is interpreting the slope and the intercept of this line. And then I'm going to go back and show you your calculator in a second, okay? So if you look here, the slope of our regression line is this. So I'm just going to rewrite our line. So remember, in mathematics, a slope is a rate of change. Okay, so what the slope tells us is this. When x changes by 1, we predict or estimate that y increases, because it's a positive slope, by 5.0333, okay? So to put that in terms of this actual example, okay, x is hours of study. Okay, so when you study an additional 1 hour, okay, we estimate that y, which is our exam score, will increase by 5.0333. And we always actually say on average here, because some students will study for an hour and their exam score will go up more than 5 points. Some will study an additional hour and it'll go down, it will go up by less than 5 points. But on average of all the students, that's what we expect it to change. Okay, so the slope tells us when you change x by 1, how much does y change? So when I study 1 additional hour, my exam score goes up by this much. All right? Make sense?
Yeah.
So, you know, you're going to have your midterm coming up in a couple weeks. So basically what I'm hinting at here is study, okay? Whenever you do a regression equation, you can always interpret the slope. The slope is always meaningful, okay? However, the intercept is not always meaningful, okay? Sometimes it is, sometimes it isn't. That's where it's a little tricky, okay? All right, so we saw that this was the y-intercept. Okay, it's 45.0835. Okay, so when you go to interpret an intercept, you have to ask yourselves the following questions. All right, the y-intercept occurs when x is equal to 0. So is 0 a reasonable value for the explanatory variable? So meaning, can somebody study for 0 hours?
Yeah.
Yep, yeah, sure, I wouldn't recommend it. And then do observations near x is equal to 0 exist in the data set? Yeah, like we have one for x is equal to 1. Okay, so when you have both these questions, okay, the interpretation is reasonable. And basically what we're saying here, for a student who studies for 0 hours, we predict their exam score to be 45.0835. Okay, so study for the midterm. Okay, that's really, you know, for an hour, I guess that's basically what I've been saying. All right, I just want to give caution with least squares regression line. So it's used to make predictions based on values of the explanatory variable, if it is used, excuse me, for values that are much larger or much smaller than observed values, okay? What we say is that you can't do it and it's outside the scope of the model, okay? So never use least squares regression line to make predictions outside the scope of the model because you just can't be sure that a linear relationship exists. What I mean by that is if you go back and look at our original set of data here, okay? Can somebody study for 10 hours for the midterm exam? Sure, okay. Could somebody study for 100 hours for the midterm exam? What do you guys think? Could somebody spend 100 hours getting ready for the midterm?
Maybe.
I mean, they could. Yes, they could. Yeah. Okay. But so what happens is probably after a certain number of hours of studying, it just doesn't impact your exam score anymore. So like the relationship between hours of study and exam score is linear to a certain point. And then after that point, it no longer makes sense. There's no longer a linear relationship. So we only use this values or regression for values between the data, like missing values like 5, or values that are really close to the ends of data, never really far away from our original set of data. Okay. All right, so let's see. Here was our regression equation, okay? So just like with everything in this class, when we use technology, when we can use technology, we're going to. All right, so go back to your graphing calculator, okay? So remember, the slope was 5.033 and the y-intercept was 45.0835. Well, good news. Your graphing calculator will actually do this for you. So you don't actually ever have to do this by hand ever again. All right, everyone's now thinking, well, why did you show me this, Matt? But let me show you how to do it with your calculator. So go back to your calculator, hit the stat button. You're going to scroll over to calc. And this has been called least squares regression. Okay, your calculator just refers to it as linear regression. It's just another way of saying least squares regression. So the option number 4 that we used to find the correlation coefficient, I'm just going to go to number 4 again. I'm going to scroll down to calculate. And you should see this. Okay. All right, we'll look at this here. Hopefully you can see it. Okay. It's saying they call it AX plus B. Okay. A is the slope. Look at what they got for their slope. 5.033333. What did we get? 5.0333. Yeah. Boom. Look at that. You'll notice a slight discrepancy when they go B. They call B the intercept here. They get 45.0833. We got 45.0835. Okay. Does anybody know why ours is slightly different? Well, if you look back when we did this by hand, did we round some numbers off at 4 decimal places? So that's why ours is slightly different. Okay, just because we rounded, your calculator doesn't. So which is easier, by hand or using the calculator?
Calculator.
Yes. Yeah. Everybody's like, Matt, why don't you just not show us how to do it by hand and just show us how to use a calculator? But I'll be honest, it's good to know how to do it by hand. Just before we take our break, did I ever tell anybody what my first job was out of graduate school? Have I ever told you guys that? So my first job out of graduate school was working for this company called Lockheed Martin. And so what I did was I was a statistician, but half of my job was programming statistical functions. So like I had to program the calculator how to do this. And like if you don't know how to do it by hand, it's really hard to program the calculator to do this. So knowing how to do it by hand is important. But going forward, now that you've seen one example, going forward, what we'll do is we'll just use our calculator for this. Okay. All right, sound good? Everybody, we'll take a little bit break here. Does that sound okay?
Yeah.
All right. All right, so what we'll do here, we'll take a 10-minute break. And then after our break, we'll come back, we'll do another example of this, okay? Okay, so we'll start back at 10:10. So we'll take a little 10-minute break from here. Okay, everybody?
Okay.
I said enjoy your break. I'm gonna grab some coffee and I'll see you back at 10:10. All right, everybody. Let's finish up for the morning. So what I want to do now is I want to do at least one more full example here, where what I do is I just walk you through basically what your online quiz question is going to be like this week. All right. So after this lecture, you'll be able to handle at least the regression part of your homework. So as I said, if you go back into the classroom, under week 3, your post-class requirements, just upload it up. Your first couple questions on it are all going to be probability questions. So you'll have to watch the online lectures for that. But then once you get to question 6 and then on is all this linear regression stuff. And when you go to plug this into your calculator, just plug the values exactly in as they are, 1200 and 300,000. You don't need to like edit anything down, just plug them in exactly like that. And then this next example will show you exactly how to do that. All right. Before I get back to the lecture, does anybody have any questions about any of that? I hope everybody else got coffee. Okay. All right, so first thing I want to do real quick is I just want to clear the previous example out of our calculator. So go to your calculator, hit the y equals button. You should see this, the equation of the line in here. Just hit clear, enter. Okay, so it's always the clear button. Okay. Then we're going to hit stat. We're going to go over to calc, or not stat, I'm sorry, stat under number 1. We're going to edit the list. So edit number 1, sorry about that. And you want to clear this data out. So you're going to go to top of L2, hit clear, enter. You're going to go over to L1, hit clear, enter. Okay, never ever hit the delete button. All right. Who's with me on that so far? Okay, I got 1 person, 2 people, 3. Okay, good. At least a couple of you are. All right. I don't know why I like this example. I found this example, example a while ago. And it's about scuba diving. Okay. I'm just curious, has anybody ever been scuba diving before? I mean, yeah. I've been once in my life, and it was really interesting. It's fun. It's really weird getting used to breathing underwater. Yeah, I bet it's very different going scuba diving in the United States, because I bet when you go scuba diving in the United States, there's all this training, safety courses you have to take and waivers you have to sign. So I went scuba diving overseas, and they literally just put a tank on me and threw me overboard. So it was very, very different experience. Yeah. Yep. Yeah. Overseas, just whoop, here you go. Yeah. I was actually in Australia, and they just put the thing in my mouth and just whoop, pushed me right over. Okay. All right. So here's the example. So the following table has 2 variables on it. Okay. It has max dive time, okay, in minutes, all right, based on the depth and feet of a scuba diver, okay? So it looks like this is what the problem is saying. If you're gonna go scuba diving at a depth of 20 feet, all right, you can go scuba diving for 100 minutes, all right? But then as you increase your depth, okay, so the further you go down, what happens to your max dive time?
Decreases.
Yeah. So as depth increases, max dive time decreases. Okay. So the variables are moving in opposite directions. Okay. And that makes sense, right? Like water pressure, things like that. You just can't stay underwater for as long. Okay, so we have this table. Here's the first question. All right. So we want to do basically this whole thing of linear regression. So first thing it says is which is the response variable? Which is the x and which is the explanatory? Which is the y variable. So based on this example, which variable do you think, oh my God, I wrote this backwards. Holy cow.
Yeah, I noticed that. I was going to say.
Just not enough coffee. I'm only on my third cup. All right. All right, which variable do you think explains the other one? Do you think depth explains dive time or dive time explains the depth you're at? Yeah, okay, I agree. All right, the explanatory variable is depth here. Okay, so the depth you're at determines your max dive time. That's the way we're looking at it here. Okay, so how far down you go explains what your max dive time can be. All right, perfect. All right, so the next thing we're going to do is we're going to create a scatter plot of this data, all right, and comment on the relationship. So grab your calculator and we're going to plug the data back in. So if you're on the main screen, you're going to hit stat and under number one, you're going to edit the list. And remember, L1 always gets your explanatory variable, all right, which is going to be your depths here. So 20, 30, 40, 50, and 60. All right, so it looks like there's just 5 data values. So going over to L2, you're going to put 100, 95, 91, 83, and 70. All right, so right now your calculator is still zoomed or centered around the previous example, okay? So whenever you redo these problems, you just have to recenter or rezoom your calculator. So I'm gonna press the zoom button again. And I want zoom stat here. On mine, it's number 9. On the TI-83, I'm not sure if it's different, but it's zoom stat. All right, and it looks like this, okay? How would you describe this relationship?
Pretty negative linear relationship.
Yep, perfect. I agree. So the scatter plot, I'm just gonna just roughly look like this. And it looks like a negative linear relationship. All right. So the next thing we're going to do is we're going to have our calculator do a lot of work for us. We're going to calculate the value of R. So we're going to go back to our calculator and we're going to hit stat. We're going to scroll over to calc. And what option was this?
Linreg.
Yeah, we're always going to use number 4 this week, Linreg. I'm going to hit enter. I'm going to scroll down to calc. Now, if you have the TI-83, just hit enter again. And right here, it's negative 0.9701. All right, how many people, everyone seeing this? Okay, so negative 0.9701. Okay, I'm going to add a little bit to this. Let's compare to the R critical value. So if you look back here, I'm going to go back and just copy this table here a little bit. If you look here, the way you would use this table, just to confirm that there is indeed a relationship, you'd go to n as the sample size. So there's 1, 2, 3, 4, 5 values, and you'd look here. As long as the absolute value of r is greater than this critical value, 0.878, which it is, right? Like the absolute value of this is 0.9701. Like that was the cutoff value. It absolutely confirms there is a linear relationship between the variables. Awesome. Okay, good, good, good. So far, so good. Okay, the calculator makes everything easier, obviously, okay? So let's go to the next slide. Next, it says find the least squares regression line. Now, you'll notice if you downloaded the slides before class, forgive me, I added these two questions in. If you remember an hour or so ago, I said, hey, I modified the slides. It's because these two are two new questions, okay? All right, so first let's find the least squares regression line. This is fantastic news right here. Does your calculator do this for you right on the screen here? What do you guys think? Yeah, like this part right here, literally this part right here is the regression line on your calculator, okay? So it looks like A, the slope is negative 0.72, okay? And the intercept is the B value, the calculator calls it, is 116.6, okay? So find the least square regression line. All right, it's y hat is equal to the formula we had. All right, I'm just gonna call it ax plus b here, all right, using calculator notation. Okay, just so we're clear, what y hat here is, looking back at our example, it's the estimated max dive time. Or predicted dive time. Okay, and in minutes, and x here represents the depth that you're at. So if you give me the depth, I can tell you, hey, what is the estimated max dive time? So our calculator, all right, y hat is equal to the slope, looking here, was negative 0.72. Times x, okay, the depth, plus, I think it was 116.6. Yeah, okay. So this is my least squares regression line here. So much easier, by the way, than doing the doing it by hand. Yes, yes, absolutely. It's 100% easier using the calculator. Okay. Now let's interpret the slope, okay? My slope here is this negative value. Okay. So just real quick, if you remember right before the break, can you always interpret a slope for a regression line? Do you always interpret the slope? Okay, the answer is yes. The slope you always interpret. Okay, so the slope is the rate of change. Okay. And so what it says is when x increases by 1, is y going to increase or decrease with the negative slope? Yeah, because it's negative. Y decreases by 0.72. Okay, so to put this in terms of the actual problem, okay? For each additional foot of depth. Okay, so when X increases by 1 foot, so for each additional foot, okay, the max dive time decreases by 0.72 minutes. And this is on average. Okay, so basically what I'm saying is, hey, look, every additional foot you want to go down, you lose 0.72 minutes. That's the interpretation of the slope here. Okay. All right, so the next thing you have to ask yourself, is it reasonable to interpret the intercept here? Okay, so let's just go back real quick. You have to ask yourself 2 questions, right? All right, is 0 a reasonable value for X? And are there any observations near X is equal to 0? Okay. Well, can you go scuba diving at a depth of 0 feet? Does that make sense? What do you guys think? Yeah. What? Like someone says, hey, we're going to go scuba diving at a depth of 0 feet. It's like, what? You know, that doesn't make any sense. That doesn't make any sense, obviously. And there's no values close to X is equal to 0, right? And so like, if you think about it, when X is equal to 0, Y hat is equal to 116.6. So what we're saying here is like, another way to think about it is, does it make sense to say, hey, when you want to go scuba diving at 0 feet underwater, your max dive time is 116.6 minutes? It's like, no, that doesn't make any sense. Okay. So for this example, it is not reasonable to interpret the intercept. Okay, just not reasonable to interpret the intercept. So it just depends, depends on the context of the problem. Like I've done one example where it is reasonable and one where it isn't. You just have to like think through the problem, right, if it makes sense. Okay, at least finding the regression equation pretty easy. I hope so, yeah, okay. All right, let's do, let's just do these 2 examples, these 2 questions right here. All right, so let's estimate the max dive time at a depth of 55 feet. Okay, so this is the equation we had. We had y hat is equal to minus 0.72 times x plus 116.6. Okay. There's 2 variables here. There's y and there's x. I'm giving you the depth at 55 feet. All right. Which variable am I giving you? Yeah, thank you. So all you have to do when you're given x is you plug into the equation. All right, so wherever I see an x, I'm going to plug in 55. So unfortunately, I actually didn't work this out ahead of time, so I need to grab my trusty calculator. So it's minus 0.72 times 55 plus 116.6. Did anybody else get this value here when they did this? All right, yeah, wow, great. Okay, so if you want to go at a depth of 55 feet, okay, what we're saying here is, you can go for 77 minutes. And like if you look back here, 55 is somewhere between 50 and obviously it's between 50 and 60, and 77 minutes is between 83 and 70. Okay, so it makes sense. It works. All right, now this one here. At what max depth, all right, could you dive for 60 minutes? Okay. So what I'm asking you here is I'm asking you to find depth. Okay, yes, thank you. Perfectly in the chat there. So the variable I'm asking you to find here is I'm asking you to find x. Okay, if you're going to solve for x, I need to give you y. Okay, and I do tell you that. I say, okay, if the max dive time is 60 minutes. So we're given that your estimated max dive time here is 60 minutes. Okay. Is that the answer, Heather? I haven't worked it out yet. Well, hold on. No. So I'm asking you to find X here. Okay, so you're given 60 minutes. So yeah, thank you. Yeah. So I'm going to replace this y hat with the 60 minutes that you're given. So this is the y here is going to be replaced with 60. All right, so now I have to just solve this simple linear equation. All right, so what am I going to do to solve for x here? What's the first thing I'm going to do? I'm just going to subtract this over. It's a simple linear equation. Yep. So these cancel out. I think you get minus 56.6. Did I do that correctly in my head? Believe it or not, I'm really like terrible at math. That's a joke. That's a joke. Yeah. Okay. Then the next thing you're going to do is you're going to take this and you're going to divide. Like this. Here, these are going to cancel. A negative divided by a negative becomes a
Positive.
Yep. So just going to take this negative 56, divide it by negative 0.72, and you get this answer right here, which is 78.61 repeating. So I'll just do it as 78.6. So this is what I'm saying. Look, if you want to go diving for 60 minutes, you can do so at a depth of 78.6 feet. Make sense? Yeah, and just so you can see that all this worked out, I should have did this prior. But like, let's just plot our line over our data again, just to confirm that this line definitely fits the data well. So like, I'm going to go back to y equals, and I'm going to plug in my slope, which is negative 0.72. So don't ever do the subtraction sign. Use this negative 0.72 times my variable plus 116.6. And when you graph this, yeah, like you see, like the line fits the data really well. All right. What do you guys think? Not too bad? You could handle this?
Yeah, it's good.
Anybody else? Good. Any last? So we don't have time to do the next question, so I'm actually going to end class about 10 minutes early here. But I'll stop the recording, and then I'm going to stick around. And I know there was a calculator question, and then I'll answer any other questions anybody has. So let me just stop the recording.